Okay, hi everyone. How are you today? Good. I'll give you a chance to answer, just stay good. So let's see, the problem set for Friday, you saw that hopefully, about some of the row reduction stuff we did in class on Tuesday. Today I wanna move on to start, I sort of mentioned that we were looking at rows of a matrix and thinking about that as like systems of linear equations, right? And now I want to move to this different perspective, which is thinking about columns of a matrix as vectors. And so I want to do some vectory stuff. Oh, you know, one thing that I've been meaning to talk to you about, and actually put a link to. There is this one YouTube channel I really like for math videos. Most I don't like, but this guy, this 3 Blue 1 Brown channel has this video series called Essence of Linear Algebra. And these are beautiful videos, and I definitely recommend. I'll try to like put them as like suggested assignments. Nothing, I don't think is anything that you like necessarily have to, like I'm gonna force you to watch, but like just so yeah, this you can sort of see, first off, he's got the little pie creatures as his little mascots, which is fun. But so he talks about vectors as lists of numbers, as arrows that you can sort of like move together. And then the big thing we're gonna do, as I think I mentioned last time, we're gonna write vectors as columns. And when you add, how do you add vectors? You add entry by entry, right? So you're just gonna add across in rows, and you can scale vectors by numbers, right? So like if I want to scale a vector, I just double its length. I just double each of the entries, or if we're in 3 dimensions, all 3 of the entries and stuff, right? I like that. Mathematician will ignore him for now. So that's the first thing, is just to like think about, and then like again, just watching these videos, you'll see a lot of like it's just it gives you all of the geometric insight. They're just very well done. And then here's some like 3D pictures, and then I'm doing that horrible thing of just like clicking through the video, but anyways, so you'll get the idea. So I'll try to put a link to this, but if you Google like 3 blue 1 brown, it's a weird, I think he said his eyes are apparently 3/4 blue and 1/4 brown, which is strange, but that's why he called it that. But yeah. And look, there's merch. I support him on Patreon, so I'm giving him money already, so that's good. But I could buy some merch. Anyways, this is a great series. Like I said, I'll try to remember to like suggest, because even the stuff we're gonna do like today and next Tuesday has a lot to do with this second video, which is about basically like thinking about all the different possible linear combinations of 2 vectors, like scaling and adding. There's like a v and a w, and he's sort of doing all possible. You can faintly see the original v and the w in the background there. And so we're going to talk about a lot of that stuff. You know what? I never changed the share. So for the video, for the recording, they didn't see any of that. Sorry, they're just looking at this. Oh, I'm so bad at this technology. Okay, so anyways, back to this handout. That's the main important thing. I'll put a link to the 3 blue 1 brown videos. So sorry for messing that up recording, but the idea is going to be that, right? So we're gonna care about vectors as, we're gonna move into group work very quickly actually here today, because I really want you guys to just work through examples and play around with stuff. But we might do the first couple together. So we're going to write vectors as these sort of as abstractions. We're going to write them as these bold letters with arrows over them for vectors. Rn or Rm is supposed to be n-dimensional real space. So like, let's just say vectors and linear combinations. So Right, we write, so R sub R to the nth power is n-dimensional real space equals a set of all sort of n-tuples where each xi is a real number. So we have R2 is the usual xy plane, and R3 is 3D space, you know, XYZ space. A lot of times we'll use X1, X2, X3. We'll use subscripts instead, because we want to be able to think about generalizing this kind of ideas, at least to like, what if we were in 14 dimensions, you know? So we'll use these a lot. So a vector, vectors in Rn, in this class, written as column vectors. As column. I mean, they're called column vectors. They're written as columns. So for example, the arrow from 0, 0 to 3, 2 is written, you know, vertically, 3, 2. Right? We're just going to write that. If you remember from multivariable calculus, there's the ij and ijk notation, right? So we could also write, so you can write it as, I mean, the way, you know, we can also say this is written as like 3i plus 2j. And I could draw a picture. I should draw a picture. So if we have the x and y axes, we have this vector I, which is really the 1, 0 vector. We have this vector j, which is the 0, 1 vector. And so when we say 3, 2, we mean we go over 3 of these, right, and up 2, and we draw that arrow to that point. Oh, I don't know if I can still do that. I used to have the skill of like drawing the dotted lines on the board. I might have practiced it way too much before I went to that. Oh, I can't really do it as well as I used to. Okay, so that's 3, that's the point 3, 2, right? And so this is, we could say V is 3, 2, or we could say it's 3i plus 2j. But notice we hopefully that makes sense, because we could break this up, or maybe I should say this. We think of V as, you know, from multivariable, we rewrote V this way. But if you think about it, that's 3 times the vector 1, 0 plus 2 times the vector 0, 1, like that, right? And that's just, but we can multiply the 3 through here. So that's 3, 0 plus 0, 2, which is 3, 2. So that's kind of like the general way we write these things down. Not saying anything that, I mean, you just think this notationally, but also it works mathematically if you replace I with 1, 0 and j with 0, 1. And in 3D, we'll have like 0, 0, 1 for k, right? So these are the basics. And then I guess what I wanted you guys to do, so, okay, so maybe back to the screen share, the screen for a second. So a linear combination of vectors is when like you add and scale, you like basically scale vectors and then add them together. That's called a linear combination. And what we're gonna ask a lot in this class is like, what if we take all, like give you a couple of vectors and like, what if we take all possible linear combinations? What do we get? Do we get the entire plane? Do we not get the entire plane? If we're in 3-dimensional space and I take 2 vectors and I ask you for all linear combinations, what does that make geometrically? We're gonna think about that. Not significant the answer now, but we'll think about that. So we're going to ask this question about like this bullet point 1 here, about what do they generate? And we're also going to ask about, like, is there redundancy? Like if I gave you 3 vectors in the plane, you could somehow probably throw one of them away. Like if I gave you I and j and v and said write some other vector in terms of those, do you really need v? No, because you can write it in terms of I and j. So like throwing a v in would be redundant, so that would be called, it's what's called linearly dependent. And so we're trying to like, there ends up being a Goldilocks game where you try to have like enough vectors to generate everything, but not too many vectors so that there's no redundancy. So you're trying to just adjust right sort of thing. And that's something we're going to look at. This is all like preview. So if it sounds kind of abstract, it's okay. Yeah, so just about these specific, I mean, we can talk through 1, 2, and 3, or yeah, 1, 2, 3 quickly together, and then I'll let you guys, I'll put you guys into groups to work at the boards, starting for number 4. So if you have a device, you might want to pull this handout up on the device. It's the linear combinations of vectors. It's the second handout on the handouts page. Right, but let's just start with just to talk through a couple of basic things together. Linear combos of vectors handout. Am I screen sharing still? I am still screen sharing. Screen sharing the whole time, who knows? Vectors handout. So number 1, so what it says, let v, what does that say, v1 and v2? v1 is 3, 1, and v2 is 4, -3. Okay, v1 is 3, 1, v2 is 4, -3. So the first thing is just to say like what a linear combination is. So if I wanted -2 v1 plus, what does it say, 5 v2. Take a second and compute that. I want to multiply the first vector by -2, the second vector by 5, and add them together. So what did someone tell me what they got? 14, -17. Okay, -6 plus 20. Okay, that's good. -2 minus 15 is -17. Okay, so that's the thing. It's just that's what you do to take linear combinations of vectors. You just scale each one and add them together. Right. For number 2, we kind of talked about this a little bit, but like, right, that I and j are kind of these 2 fundamental vectors that we use to generate everything, right? So basically what I'm thinking here is kind of what we did up here, which is if we want to take xi plus yj, then we could write that as x times 1, 0 plus y times 0, 1, and then write that as the combination x, y. So every vector, so starting with any x and y, we can write it as a combination of I and j, right? I'm sort of thinking about going this way with it, like if I start with. So that's the idea, sort of, that's what it means when I'm saying every vector can be written as a linear combination of 2 special vectors. And the 2 special vectors here are I and j. And that you're totally used to that, just in the xy plane going parallel to the x-axis and parallel to the y-axis, right? Moving around, right? Okay, so that's not controversial. I wanted to talk about number 3 just because it's kind of funny. And then I'll put you guys in the group work starting for number 4. we're going to start thinking about all the linear combinations. Like we're going to think about all the possible linear combinations of these two vectors. And I just wanted to note that like V1 itself is a linear combination of V1 and V2. How is it? How can I write? What number can I scale this by and scale this by and add them together to get V1? 1 and 0, yeah. So it's worth mentioning that, like, so just note, it's kind of goofy, but note that V1 is 1 V1 plus 0 V2, and V2 is 0 V1 plus 1 V2, and even the 0 vector, we can write as 0 V1 plus 0 V2. So like you get certain vectors and then you can start thinking, but you can also get all multiples of one vector of V1 just by scaling V1 and having no V2s, you know, and so on. Okay. Like I said, not a trick question, just something worth noting. So number 4, it says, let's look at another vector, 2, 5. Can it be written as a linear combination of the V1 and V2? And I claim this turns out to be a linear system that you're trying to solve, and that we're going to connect it back to linear systems that way. And so we can also turn it into matrices and stuff. So what I want to put you guys into groups and use the boards and start from number 4 and just work for a while. That'll be fun. How should we do groups? What did we do that way? We did it on Gather, right? We did group work on Gather before. And you guys just went and found rooms. I just like throw you guys into groups. You 3 want to work with that board? Wait, how many people do we have? Like 20, wait, 3, 6, 9, 12, 15, 18. Probably, wait, and then we really have like, maybe like 5 boards. So maybe I need groups of like 4. So you 4 back here want to work kind of over there maybe. And yeah, the 4 back there. Sorry, I don't know if you wanted to work with. You got to meet people. So you 4 in front of me. You guys want to work up here? You can use my special chalk at the front board. You 4 can work over there, and then you 4 can work over there. That sound good? And so about group work, just one thing I would say is like, switch off who's at the board, because probably people want to write stuff down on their notebook, what we're doing. And so you want to give a chance, so not have one person have to write everything down on the board. And then be nice to each other, introduce yourselves, say your name, what year you are, if you're a team. Try to make it comfortable enough that if somebody doesn't understand something, they're going to feel comfortable asking the others to like slow down and explain it. Because I've seen groups where just like 1 or 2 like speed demons go riding off into and go fast, try to go through everything as fast as possible, and it's demoralizing for the other ones. So you know what I'm saying? Just be decent to each other. That's all I'm saying. I think one year I was like, just don't be an asshole, and then I actually called a kid an asshole. I was like off the crossroom. I was like, "You're being an asshole," because he was like just racing ahead, trying to do every problem and leaving his group behind. And we had a good laugh about it at graduation, like 3 years later. So okay, so don't make me call you an asshole, is what I'm saying. Okay, so yeah, let's go to the boards in those groups and start working number 4. I'll pause the recording. And we'll do that for a while. We may do that most of the rest of class, and then just come back together and say some general things. So great. Okay, good job. I just want to make a couple comments about sort of what you guys did on some of these problems. I think you have to dive into the nitty-gritty, but it's sort of an interesting thing here, right? Like, let's look at the 2-dimensional case first. Yeah, so right, so no, I don't want to be on screen. So for the 2D case, what were the vectors again? They were, sorry, I can never keep these vectors in my head. 3, 1, and 4, -3, right? So the 2D example, V1 equals 3, 1, V2 equals 4, -3. And you actually found that not just this specific W, but every vector can be written in terms of V1 and V2, right? Like it's possible to generate every vector. And in fact, so you found when you row reduced, right, when you row reduced, I mean, so when you think about like x v1 plus y v2 equals some specific b1, b2, right? Let me just call this b. So we found we could always solve this. We can always solve this for any b, for any choice of b, right? And you actually got, yeah, if this is b1, b2, what did you guys get? In fact, when you row reduce, so you did, basically you row reduce this matrix, right? And you end up getting, what did people get here? It had the stuff that had the 13ths in it. Someone tell me the numbers again. 3/13 or something. 3/13 B1. Plus or minus? Plus 1/13 B2. And this ended up being 4/13 B1 minus 3/13 B2. Okay, so that's interesting, right? So this is really X. And this is really Y, right? And I mean, actually, if you translate these back to X, like this becomes X equals that, and this becomes Y equals that, right? When you translate back to equations, that's why that's happening. I did want to notice something that's sort of, I think, fascinating. These four numbers kind of make a matrix themselves. In fact, there is a way you could have thought of making B1 and B2 variables and actually just making this like a 2x2 matrix. You could do that, you know, you could sort of think, because we have X and Y over here and we have B1 and B2 over here. So you could do that. And I just want to point this out just as like a thing to think about. If we actually wrote this array of numbers and I pull the 13ths out, we get 3, 1, 4, -3. Just compare to what we started with. I just feel like there's something interesting happening there. It's like almost the same, except what? Yeah, we sort of swapped the 1 and the 4. That's interesting. That's an exclamation point. Another exclamation point, and then we'll make a smiley face. So yeah, there's something interesting going on there. These numbers are not an accident. There's also something, have people heard of the determinant of a 2x2 matrix? It turns out, we're going to talk about this obviously in the semester, but you do AD minus BC, you do like this times this minus this times this. If you do that in this case, what number do you get? This minus that. So -9 minus 4, -13. 13. That 13 actually has to do with the determinant. And these numbers, so they're predictable. It's an interesting thing. And we could have predicted all of this, is my claim, without doing all those horrible computations that you did. So nice to think about for the future. There's a way to do this stuff. So that's just kind of putting that out there. But in particular, the B1 and B2 actually, like, they span all of the plane, because we can write any vector in the plane. And in fact, I think I have, yeah, I think I actually made some pictures of this. And let me share screen also. Yeah, so V1 was the vector 3, 1, V2 was the vector 4, -3. And if you draw, so like you can draw this like V1 axis here and a V2 axis sort of. You could have done that, and then you can sort of see where this is W, the vector that we care about, the 2, 5. And you can actually see that you do two V1s and then a minus V2, and it'll get you there. Does that make sense? So it's all visual too. You can also do this all visually and see it that it's right. And in fact, I think I also did an exam, just like, I think I drew this picture sometime of like, this is clearly after I got the iPad right and I could draw nice things on the, wait, let me switch the share. So you could also, yeah, I think I zoomed way in and I made this by 13ths. I made this like 13, and then this is like 4 V, or I is, this was the this was the V1 axis here, and this was the V2 axis there. And I think you can tell that that maybe this is scaled. Everything's scaled down by 13, and then there's a certain, it's not super obvious, but in terms of how you wrote I and J in terms of V1 and V2, you could sort of check that this works from this picture. And like, so it's checkable geometrically also if you draw the picture carefully enough. So anyways, that's not, at a time, I don't want to spend too much time on that. But okay, so that's just an interesting thing to think about already, that like, that we don't have, that we have like, that these two vectors span everything, that they cover the entire plane. Now in the 3D case, that didn't happen, right? The 3D case, well, some of this on the board. So in the 3D situation, yeah, there was some stuff that ended up happening down here that when you row reduced, so like back in the corner there, you guys row reduced with the -1, 1, 1. Here, let me scroll down to the vectors. Oops. Yeah, so you actually got, so when you solve that, you actually found a free variable, right? So Z, you could get X and Y in terms of Z. Z was free. You got this whole row of zeros. If that hadn't been 0, there would be no way to write the W as a linear combination of those 3, right? But you got all zeros, and so in fact, there's infinitely many ways to write W as a linear combination of those 3 vectors. But particularly if you take Z equals 0, you get like a half comma negative, or -3 halves comma a half is one way to do it. So that's interesting. So then the 3D example, V1, V2, V3, this set of vectors does not span, this is the word we're going to use, span all of 3-dimensional space, right? If you think about it, if I had 3 vectors in space, you kind of try to start pointing out in the air and stuff. If I have 2 vectors like this, and a third vector pointing out the top of my head, does that feel like that spans all of 3D space? Could I sort of get everywhere? Oh, maybe not, I don't know. But like when we take I, J, and K, that spans all of 3D space, right? Because we can always move like in the X, Y, Z directions, right? Like we can move a certain amount in the X, a certain amount in the Y, a certain amount in the Z. I guess my question is, how are you going to fail? It feels like if you have three vectors that you can sort of go in 3 different directions, you should be able to get everything. Right, so algebraically it shows up as not having all 3 pivots, but geometrically, what's true about the relationship between the vectors? Like, can anybody guess? They're all perpendicular to each other? Well, I, J, and K are all perpendicular to each other, and that's a good thing. So we don't want that somehow, right?
If it doesn't span, 2 of them will be the same one.
Well, these weren't, but these 2 were not the same vector. I mean, it's interesting, right? If we got 2, yeah, if we had 2 of the same vector, that definitely wouldn't span everything. What would just 2 vectors span? Yeah, a plane in space. If you just had 2 vectors, they would sort of sweep out a plane. So the third vector didn't add anything to it. So what do we know about that third vector? Yeah, it lives in the same plane. So it turns out that these are all coplanar. V1, V2, V3 all live in the same plane. And that's why they don't span all live in the same plane. That's why they don't span all of 3D space. It would be like here if, kind of what Ronaldo said, if it'd be here if we like had, in 2D space, if we had two vectors like opposite of each other, then you couldn't leave this line, right? We need two vectors that don't point in the same angle so that we can actually get everywhere. In 3D space, we have this, they all live in the same plane. One question you could ask is, what's the equation of that plane? And you guys actually solved the equation of that plane. When you did, at least the groups who got through the B1, B2, B3. We were having fun over here, right? So when you did the B1, B2, B3 augmented column, did this end up being the correct final answer? No? Where was it? Was it here? So you guys found that, and I can rewrite that. So it turns out that if you augment with the general B1, B2, B3 column, that you end up with all zeros on the bottom. And so we're gonna actually start saying things like this. We're gonna have like the columns like this. And then that row reduced to something that was like 0, 0, 0. And then, you know, B's, there's B's here, there's B's here. And this ended up being something like 2B1 minus 3B2 plus 5B3, something like that. And so in order for this to be a consistent system, you need this equal 0. And so this equals 0, but that's the equation of a plane. And in fact, you can exactly tell this equals 0. This is the plane where all these vectors live. Basically, the W, negative 1, 1, 1, satisfies this equation, so it lives in the same plane, so it can be built from those three vectors. 1, 0, 0 does not satisfy this equation. That's what number 9 asks. If you try it with 1, 0, 0, you get 0 and non-zero here. And so that doesn't work. So it's kind of, that thing we're gonna start talking about basically is like, given our set of vectors, do they span the whole space? Do they only span like a plane? Do they only span a line? That's the kind of questions we're gonna be asking. And then how to write down what the span is. So like, we could describe the span as by this equation. Because we know a vector lives in this plane. We know a vector is in the span of this if it satisfies the equation. Make sense? Sorry, I think I'm just at 105. Okay, perfect. All right, we'll call that a day there. Good job, team. Good group work. If you can